Okay, thank you everyone for joining us today. It's my pleasure to tell you about the NeXUS project and the capabilities. So after my talk, we'll proceed to the exciting part of the program to hear from our plenary speakers, Anne Louis and David Oshalom. I won't pause after my talk for Q&A because those of you interested to ask questions or pitch ideas for use at the facility, we invite you to stick around for the virtual coffee hour that will follow. And there you can ask questions of the NeXUS team and share ideas with an in-person panel who's here tasked with writing a report. So one of the aims of this workshop is to coalesce a user community around the NeXUS facility and the experimental capabilities that it offers. And we'd just like to emphasize your feedback is welcome. We hope many of you will choose to become users at the facility. So for those of you who are joining us only online, I just want to make you aware that the workshop also includes 4 in-person focus groups in the following areas of attosecond electron dynamics, liquid phase and interfacial chemical dynamics, quantum materials and condensed matter physics, and dynamics in biological systems. So we have approximately 20 panelists spread across these 4 groups, and they're going to spend the next 2 days evaluating first science opportunities to be performed at the NeXUS facility. And so we invite you to share your questions and also ideas with this group during the virtual coffee hour. To introduce the NeXUS project, I should first back up just a little bit and tell you something about the identified need for mid-scale research infrastructure. So in 2018, the National Academy wrote the report that I'm showing you here titled Opportunities in Intense Ultrafast Lasers. And to summarize, one of the major findings of this report is identified that there are important science opportunities that fall in a funding gap in the US. Basically, ideas that are too large to support in an individual PI lab, but smaller than a full large-scale facility. And this was the concept of mid-scale. And that particularly in the area of ultra-fast and high-intensity laser science would significantly benefit from investment in this important area. So fortunately, the NSF had a vision to help fill this gap. And this led to the creation of this concept of mid-scale research infrastructure as one of NSF's 10 big ideas. And 2019 was the inaugural year of the mid-scale research infrastructure program. And it's an investment decision designed to bridge exactly this gap. So in 2019 was the first round of funding for this program. And there were 10 awards given. Of these 10 awards, 3 of them were designated design proposals. So the idea to, design infrastructure. 7 of these were implementation. So 7 facilities came out of this first year of funding. Of these 10 awards made, 3 of them are in the area of so-called extreme light or ultra-fast and high-intensity optics, of which one is NeXUS with a focus on ultra-fast. There's also the zettawatt equivalent ultra short pulse laser, or ZEUS, at the University of Michigan, and the compact X-ray free electron laser at Arizona State University. So I think it's significant that of these 10 awards, 3 focus on the concept of extreme light. And I'll reiterate what Kelsey said, that NeXUS is the first and to date only mid-scale award administered by the NSF Division of Chemistry. So what is NeXUS and what will its capabilities look like? So at the heart of NeXUS is a kilowatt class ultra-fast laser that will produce a range of light spanning from 8 millijoule pulses at 100 kilohertz to fraction of a millijoule pulse at megahertz. Repetition rate pulse duration will be as low as 8 femtoseconds. And then the purpose of this laser is to drive attosecond, femtosecond XUV soft X-ray generation for XUV and soft X-ray spectroscopy. And so this light source will supply customized light to a variety of experimental characterization stations, which include X-ray absorption and X-ray reflection, angle resolved photoemission spectroscopy. There'll be a beamline devoted to element-specific resolved scanning tunneling microscopy, and then a 4th end station, which is devoted to attosecond science and laser-induced electron diffraction. So I can say a few words about the rationale for using a kilowatt class laser to drive XUV generation in this manner. I'm not going to say very much about the process of high harmonic generation. Actually, our first plenary speaker is largely responsible for the development and observation of this. So you'll have the opportunity to hear from someone who knows this extremely well. But what I would like to emphasize is that high harmonic generation, it's an extremely nonlinear process that relies on the ionization of gas and then the acceleration of electrons by the intense laser field. And what's important to keep in mind is that you can reach saturation in terms of the amount of XUV photons that you can convert in a pulse at relatively low pulse energy. So a few millijoule laser pulse is sufficient to saturate that conversion efficiency for the high harmonic generation process. So when you talk about how can you generate a very bright XUV source by high harmonic generation, you don't want to necessarily scale the laser pulse. What you want to do is have pulse energies on the order of a few millijoules at as high as possible a repetition rate. So this is a motivation for implementing a laser with high average power. And so our goal is that this would provide a transformation in throughput, which will enable user science at this facility. So let me just kind of give you a current comparison point. So in a number of laboratories, including my own, we do spectroscopy with a high harmonic generation light source. We use a titanium sapphire laser and we operate the spectrometer at 1 kilohertz repetition rate. And my students will tell you that many of these experiments require data averaging, far over 10 hours per sample. And when you scale this and we drive high harmonic generation with a kilowatt, now you can achieve the same XUV conversion, but with a repetition rate of 100 kilowatts. That 2 orders of magnitude is really dramatic when you consider the sample, the sampling rate. So in other words, what would require more than 10 hours of data averaging at a current instrument could be done in less than 10 minutes at a NeXUS facility. So this increase in average power will do 2 things. One is it will make experiments that are currently heroic or extremely challenging somewhat routine, and then it will enable new class of experiments. Things that can't be done due to low count rates can become possible at the NeXUS facility. So the light source will actually deliver somewhat customized XUV light to 3 different beam lines, and let me briefly describe these to you. One is a narrow band beam line. This is kind of tailored for high resolution photo emission spectroscopy. This beam line will operate in 2 modes. One, which will be a multi-megahertz repetition rate. In that mode, the time resolution will be approximately 300 femtoseconds, or it will have a second mode where you can sacrifice energy resolution, but for this cost, increase your time resolution down to 40 femtoseconds, and this will be performed only in 100 kilohertz repetition rate. You're going to be an intermediate band light source, and this light source is tailored for element-specific resolve scanning tunneling microscopy. The idea is that when you illuminate the junction between the STM tip and the sample with X-ray light, you can induce an element-specific contrast in the tunneling current if you illuminate above or below a band edge. So in this case, you're looking at energy resolution that would be sufficient to scan on or off of element-specific resonance. So this will operate at about half an EV spectral resolution. There'll be 2 modes of operation, one with a 40 femtosecond time resolution and one with an 8 femtosecond time resolution. And then the third will be a broadband light source, which will support the fastest time resolution from 50 femtoseconds down to sub-femtosecond. And this very broadband light source will range from 10 to 300 EV photon energy and have and be used for X-ray absorption spectroscopy and also for laser-induced electron diffraction. So this is a rough overview of what the laboratory looks like. It consists of a number of commercial equipment. At the heart of this is the kilowatt class NeXUS laser that I've been describing to you. There will be multiple stages of nonlinear compression in order to tailor the light for the different end stations that I'm describing. And then the angle resolve photo emission spectrometer and scanning tunneling microscope. These are commercial end stations. We also have a large number of custom components, so things that we're not buying off the shelf that are being designed and built in-house by the NeXUS team. I'd just like to kind of highlight some of the progress during the early years of the project. So it was only about a little over a year ago that the lab was essentially a storage facility. And okay, we hesitated to host NSF for a site visit at this time, but you see that in the last year and a half, I'll show you some snapshots of a time-lapse video that we have. This lab has transformed, and I'll highlight to you the broom. I'm not sure if you can see it in the top left corner of this photograph. That's really good news, because what that means is that graduate students are mopping the laboratory, and it now meets the specs of a class 10,000 clean room. So this was a big milestone for the NeXUS project. And the lab, actually, this renovation project spans more than just the primary laboratory. So there's a laboratory plus the support space. So there's extensive support space designed to enabling these experiments, which includes, vacuum capabilities, gas delivery, chillers, airlock entry for gowning for clean room status, and then also a control room where users will be able to sit and observe in real time and manipulate experiments, observe results, and analyze data in a safe environment, while not gaining exposure to this kilowatt beam. So I just like to provide a shout out to the Ohio State University for supporting this project. Actually, when this kicked off in 2019, it was just when the budget impacts of COVID was hitting the university. And at that time, before COVID, the original completion date was scheduled for February 2021, and we actually completed in July 2021. So, okay, most construction projects have longer than that delay, even without COVID. So this was really strong support by the university. And you can see that we have, here a laboratory which is really coming together. So of the end stations, 2 of these are actually installed and functioning currently. So this is some data which has been collected by Seth Shields. He's a graduate student running the scanning tunneling microscope end station. And here you see the herringbone pattern reconstruction on a gold 111 surface. This was measured at NeXUS at about 30 Kelvin a few months ago. The angle resolved photo emission spectrometer is also installed and functioning. So here's some data is collected by Shiyu Chang, who's a graduate student running the ARPES instrument. And here what you're looking at is the band structure of epitaxial graphene grown on silicon carbide measured by this spectrometer. There are other end stations which are under construction. So here I'm going to highlight the X-ray absorption team. So this dedicated group of graduate students and a postdoc have designed a sample chamber that will accommodate X-ray absorption performed in a transmission mode, also in a reflection mode, and variable angle reflectance. And so this will provide basically 40 femtoseconds down to a few femtosecond time resolution for X-ray absorption spectroscopy and accommodate kind of a wide range of sample configurations. And then there's a 4th end station, which is being built in custom. This is being led by graduate student Dina Aisa, and also a collaboration with Cosmine Blog at Kansas State. So this is going to be an attosecond electron spectrometer. It's going to provide time of flight spectroscopy at 200 kilohertz sampling rate. And this end station will also be compatible for laser-induced electron diffraction for real-time molecular imaging. So I'd like to kind of review for the benefit of you as future users what the actual specifications of these beamlines will look like. So beginning with the photo emission spectrometer, this can provide time resolution to look at dynamics as fast as 50 femtoseconds. When operating in real space mode, the photo emission electron microscope provides about 50 nanometer spatial resolution. Or when operating in momentum mode, you can achieve spatial resolution down to a few microns. Energy resolution of the spectrometer is a few tens of millielectron volts. There's going to be an ultra high vacuum suitcase for users who desire to prepare their own samples at some facility and then transfer these to the NeXUS system under ultra high vacuum. And it also provides cryogenic cooling down to 9 Kelvin using liquid nitrogen, liquid helium. This is going to take advantage of the beam in a few different configuration modes. So laser mode 1, this is going to be the full 800 watts of the laser at a 30 femtosecond pulse duration, about a 1 micron central wavelength. And when run in this mode, will produce XUV light from 10 to 70 EV and at a multi-megahertz repetition rate. And photon flux on the sample will be on the order of 10 to the 9 photons per second. In mode 2, we'll be able to achieve faster time resolution. So a fraction of the power will arrive at a 40 femtosecond pulse duration and still 1 micron central wavelength. And then we'll run experiments at 100 kilohertz sampling rate and have photon energies up to 100 eV. And one of the primary advantages of running this end station in mode 2 is not just the faster time resolution, but then you can do optical pumping of your samples with a broad wavelength of light. So OPA will generate wavelength spanning from 330 nanometer to about 2 microns. And this also is delivered at 100 kilohertz repetition rate and will be time synchronized with XUV source for pump probe experiments. Okay, moving to the X-ray absorption beamline. So here we'll be able to accommodate samples in either transmission or reflection mode. Reflection will be tunable angle, and there won't be a need for any venting of the sample chamber or kind of minimal realignment of the spectrometer. So you'll be able to make measurements as a function of variable sample angle relatively easily. This could be advantageous, for example, for depth profiling. Photon energies will be up to 300 eV with 100 millielectron volt spectral resolution in the spectrometer. And here there's really 3 different modes that you can run the experiment in. One will be a 8 femtosecond mode, where you can both pump the sample and probe the X-ray absorption spectrum with approximately 8 femtosecond time resolution. And here optical excitation will be either at the central wavelength of the laser fundamental or at second or third harmonic. We can also run the experiment in a 40 femtosecond mode, and either of these modes are going to be compatible with optical excitation from an OPA, where you can pump the sample between 300 nanometers or 2 microns. This end station is also going to have a separate chamber for a flat liquid sheet, where we can achieve liquid sheet thicknesses down to approximately 200 nanometer for looking at X-ray absorption in the liquid phase. And the time resolution of the delay line interferometer will be approximately 10 attoseconds, so extremely high resolution. So the time resolved scanning tunneling microscope beamline, this is going to have a temporal resolution of approximately 50 femtoseconds, a probe energy up to 250 eV. And the idea is that here the XUV light can be tuned above or below a resonance. And so you can achieve, I already showed you an image where we achieve atomic spatial resolution, but then the goal is to couple this atomic spatial resolution with element resolved contrast by virtue of the XUV illumination, and then to couple that with pump probe measurements of specific elements. And this end station can operate down to 11 Kelvin, and it utilizes a closed cycle cryostat, so there's kind of no cost or consumption of liquid helium. Okay, to give you a sense for the time frame of this project, this is a 5-year project as funded by the National Science Foundation, which began in September of 2019. So we're almost exactly at the halfway point of the project now. And as I showed you, the progress that's been made to date has been primarily in the lab renovation, a huge amount of design and engineering work by graduate student and postdoc teams, and some really dedicated professional staff. A lot of purchasing for acquiring the commercial end stations, which I highlighted to you, and the laser as well, and then the acquisition and assembly of all these parts for custom components. So where do we sit now at the project? So the next 6 months to 1 year are really going to be devoted to assembling and commissioning the system, which we call system integration. And then we enter this exciting phase of science validation. So that's this idea that over the next 2 years, we would really like to garner feedback from you as a user community as what are the experiments that should be done, both to demonstrate the unique capabilities of the instrument, but also to showcase its utility for the communities that will ultimately become the users. So if we look at what will happen, we're looking at the laser installation, which is scheduled for the fall of this year. And that will coincide with beamline assembly and alignment. And we expect to have the first XUV light by the end of this year. And then instrument acceptance and testing will occur early in 2023. And by next summer, we hope to begin this phase of science validation. So really the time is at hand to define these experiments. And then when the project ends in 2024, the project essentially transitions to a open user access operations and maintenance phase. So what does this look like in the long run, and why would you care? So NeXUS is going to become an open access national user facility. So you can think of accessing this much like you do a synchrotron. There'll be a call. So this is the second of 3 user workshops, and in 2 years we'll host a final users workshop, which will essentially be inviting a call for proposals. So there'll be a proposal submission process. This will be externally peer reviewed. And then based on scientific impact and feasibility, users will be awarded time. And those users who receive access based on this peer review process will receive support from professional staff to come and conduct this experiment. So what does this look like? You'll be able to work closely with staff in designing and proposing the measurements, receive logistical support with travel and accommodations. You'll receive on-site access to laboratory space for sample preparation. There'll be a control room for real-time data monitoring, and then importantly, support from the staff for data collection and analysis. So the access model looks very much like what you might see at another light source. So at NeXUS, we intend to allocate about 31 weeks per year, or 65% of the annual time, to this user access mode. There's going to be some time devoted to the NeXUS staff and internal use. This is largely for developing new capabilities and testing new capabilities that will keep the facility cutting edge over an extended period of time, and then time for facility maintenance. I'd like to highlight that Linda Young has been approved by NSF to serve as the chair of the Users Committee. So in this role, she's currently helping to oversee this 2-day in-person component of the users workshop. But we envision this users committee growing, and following facility completion, the user committee is going to operate autonomously. They'll provide reports both to the OSU administration and to the NSF, who oversee the facility. And the goal of the users committee is really to ensure a user-friendly process for accessing NeXUS, and to welcome feedback by the community. So there'll be these channels of communication. Okay, I'd like to end partly where I began, by saying that, so in 2019, the NSF funded this inaugural year of mid-scale projects. And I pointed out that 3 of these were in the area of extreme light. And if you'll remember, I also highlighted this report by the National Academy of Science, particularly calling for the need of investment in mid-scale research infrastructure in the area of ultra-fast and high-intensity research. And you can see that, the NSF really did this, and these capabilities are now coming online. So you'll notice that in these complementary capabilities of these mid-scale facilities, you have high intensity at the ZEUS project, you have ultra-fast capabilities at NeXUS, and then you have access to short wavelengths at the Compact XFEL. And this actually maps quite closely, if you think about it, investments happening in other parts of the world, including the ELI project in Europe, which is actually a project with 3 different sites and facilities that are also dedicated to different types of science, but they have in common that they're enabled by investment in ultra-fast and high-intensity lasers. And so something that we'd like to highlight is that earlier this year, the NSF announced funding for an ExcelNet award, which is called XLights. So to give you a little bit of background, the ExcelNet project is jointly administered by the NSF and the US State Department. Its goal is to bring communities together and build a so-called network of networks. So this ExcelNet proposal actually consists of multiple institutional collaborators, which include the 3 mid-scales in the US awarded by the National Science Foundation, the 3 ELI institutes in Europe, and then a number of other collaborators. And so the goal here is to build an international community and to kind of understand how to best utilize these investments, and to induce collaboration across these communities. So in the end, what we hope to realize with this project is to meet the community demand for the ability to characterize molecules and materials on the shortest scales of time, and to put this in the hand of the users. And by doing so, to bolster US competitiveness in ultra-fast science, provide workforce training, and to engage and educate the broader public. I'd like to acknowledge that the NeXUS team, so just like the science capabilities at NeXUS is diverse, these are supported by a scientifically diverse group of PIs spanning multiple departments, and some really dedicated professional staff, and of course support from the NSF side from Kelsey Cook, who you heard from. But really, okay, we should not take more than a very small fraction of the credit, because this work is really being done by a very big group. So unfortunately, it's too big a group to kind of call out by name, but you see a large number of graduate students and postdocs have invested a significant amount of their education into designing and building this facility. We have a strong support from the OSU administration, an architect and engineering team who built the lab, a large number of institutional collaborators, and then advisory boards who are all making this project a success. But what I'd like to end by saying is that just this quote from the original solicitation that led to this project is that the mid-scale program was designed to respond to an identified need of a research community with the goal of enabling US researchers to be competitive. And so we'd like to thank you for your attendance today. And ideally, you know, it's your involvement in this project which will make it a success. So we invite you to remain after the plenary talks and engage with the team and panel on the virtual coffee hour. And thank you very much for your attention.